Non-isothermal plug flow reactor. This is the problem statement. Here a reaction is to be carried out in a plug flow reactor, and there are tubes in this plug flow reactor, and these tubes will be heated with the help of steam outside, and the reaction is A to B. Reactant A converts to product B, and you are given that the reactant A is fed at 1.26 kg per second. This is the mass flow rate of the reactant A, and the feed contains only pure A, and its temperature is 21 degrees centigrade. Now what you have to do in this problem is to determine the height of reactor required for 90% conversion of A. The height of reactor when the conversion of A reaches to 90%. The internal diameter of the reactor tubes is given, that is 2.54 centimeter. Steam temperature is given, and the rate constant equation is given to you, and density of the fluid is given, molecular weight is given, heat transfer coefficient is given, and it is based on the inside area of the tubes. Heat of reaction is given. This is endothermic reaction, that's why it's positive, and you can assume that heat of reaction does not change with temperature. Before we go into the manipulation of various equations, here are the notations for volumetric flow rate and molar flow rate. In the problem statements, you saw the rate constant equation is given like this. You can compare it with the standard equation. K is equal to K naught exponential minus E over RT. So when you will compare it, you will get K naught is equal to 5.64 10 power 13 per second, and activation energy E is equal to the value that is shown on the screen. Here we start with some basic formula that you are familiar with already. Equation number first defines the concentration in terms of conversion, and second is the concentration defined as molar flow rate and volumetric flow rate. Equation third is the manipulation of equation 1. Equation 4 is rate constant. Then you will put the value of Ca in equation number 4, and you will get equation number 5. Now we perform mass balance over a very small differential volume in the PFTR given, and you get this equation, and then you will manipulate this equation, and we get it in form of dxa by dv. That is equation number 6. Then from the previous equation 5, put the expression for minus RA into equation number 6, and you will get this expression, and finally you will get the expression shown on the screen. Then the differential volume is cross-sectional area multiplied by the differential height, and when you will put the value of dV into the previous equation, you will get this equation number 7. Now in equation number 7, put the expression of the rate constant, and after some manipulations you will get finally equation number 8. When our mass balance is done, we will do energy balance, and here also we will do it over a differential volume of length dz. As you already know, accumulation is equal to in minus out, and put all these values. Here one thing to note is that capital S is the surface area of the volume element of the tube for heat transfer. This is the surface area, and A is the cross-sectional area through which the fluid is flowing. Then manipulate these equations, put A dz in the denominator of all the expressions, and you will finally get this equation. Then put ds is equal to pi d dz and A is equal to pi d square by 4 in the previous equation, and you will get this equation. Finally you can see a simplified equation is there on the screen. And then from equation 5 put the expression of the rate, and you will get finally equation number 9. So this is the summary. Equation number 8 you get from mass balance, and equation number 9 you get from energy balance, and both the balances we have done in a differential volume of the plug flow reactor. Then all the numerical values, when you will put the equation 8 at 9, you will get these two equations 8 and 9. Now the things are very simple. These two equations will be solved with the help of Runge-Kutta method, and you already know that we convert those equations into Scilab functions, as you can see in the screen. These are various constants and step length you can see, and we have calculated number of iterations we will do for the loop, and final height Z2 we have taken as 400, and it depends upon you. This is the important part of the code. This is the loop actually, and you are calculating all the parameters required in Runge-Kutta method: K1L1, K2L2, K3L3 and K4L4, and finally all these values you will put in the conversion X and the temperature T, and this loop is run up to n iterations. And when you will plot the data obtained from these Scilab codes, this is the first figure you will get. This is a graph between height and temperature, and this is the second graph between height and conversion. You can see that 90% conversion reaches when the height is about 200 meter.